All right, you ready? Here we go. So last week we started the topic of lighting calculations and we talked about different factors to consider. We talked about how you measure light levels, right? We learned all about illuminance and we learned about those IES recommendations for how much light to provide for what kind of space. All right, but there's more. We're going to continue with this topic and figure out how we're going to design to achieve that particular light level. Now that we're like, okay, we want this amount of light, how do we get that? That's today's lecture. So we're going to cover two different methods to do lighting calculations. Right? One is called the lumen method, and one is called the point-by-point method. Right? So the lumen method is used for average illuminance across a room or across a surface. Right? And therefore you can see that it is good for ambient lighting. Right? How many fixtures are needed for the room, or if you have a number of fixtures, how much illumination will they provide, right? You will also see this in some textbooks called the zonal cavity method, right? So if you see those two names, they are the same thing. Zonal cavity, yes, because a room is an empty space like a cavity, like a cave, all right? Zonal, I don't know what the zonal is about. All right, so that's one way, and we're going to hit that one first, okay? The second way is called the point-by-point method, and it's more useful for determining the illuminance level at a specific point, as the name kind of indicates, all right? So we would use this for a specific focal point, like I want this particular artwork lit up appropriately, right? Or a specific luminaire. You've got this one fancy luminaire. What kind of lighting does it provide? The point-by-point method is good for accent and task lighting, right? Not necessarily ambient, but accent and task. And it can be super complex due to just interrelation of all of the different light fixtures, all the different luminaires you might have in the room, right? We're going to do just the absolute simplest case study, all right? And know that although calculations for illuminance can be done by hand, which we're doing today, all right, they're mostly done now by a lighting software package, all right? And so by inputting a whole design, you can find out what the illuminance is all throughout your plan, all right? Or alternately, you want this particular illuminance, it will tell you how many lumens you need to provide, all right? So we're going to do the simplest base case by hand, and know that if you move into the design field like our lighting designer last week, all right, you'll learn how to do it with a software package. So let's start with that lumen method, right? Remembering that this is best for ambient or general lighting. Okay? And we're going to solve for illuminance level, which means if you've got a given lighting design, you're going to find out what light level that provides, right? You've designed this 6 fixtures. What's the room going to feel like, right? How many foot candles will that provide? Alternately, all right, you can kind of work it forwards or backwards, right? Alternately, you can solve for how many lumens are needed in the room and therefore how many luminaires, right? So if you determine how much light is needed, then you can work backwards and find out how many fixtures are needed. All right, so this equation kind of works forwards or backwards depending on what type of information you're looking for. And here's the equation. It's the same one that we worked with, I guess it was 2 weeks ago, not last week. All right, same one. Illuminance, and we're defining it as the light that makes it to a surface divided by the area of the surface. And we're going to simplify that with some values. Illuminance is called the capital E. Right? So E for illuminance equals lumens divided by area. Right? That's your equation. It's not that complicated. You can do it. All right. So let's practice applying this. And the first thing we want to do is find out how much light is being provided by a given lighting design. You've got this design. How much light is it going to provide? All right. So we're going to imagine a room. It's 10 feet by 15 feet. And it's got 5 downlights placed evenly around the room. Remember, we're working with ambient lighting. Okay. Each downlight emits 1,000 lumens. And so if we assume or imagine that all of the lumens from each luminaire end up on the floor of the space, and I'm going to talk about why we might not make this assumption in a little bit, okay? But if we assume we get all 1,000 lumens, right, on the floor, what illuminance level can be expected on the floor of this room? Let's pause and let you try this. Plug in illuminance equals lumens divided by area. Yep, all the information is here for you. Let's see if you can plug this in. Some people are still writing. I'm not that hard. Here we go. That's not as hard as you're thinking, guys. All right, so how much light are we providing to this space? It's 1,000 lumens times 5 lights is 5,000 lumens. All right, yeah, you don't have to use a calculator for that. It's okay. All right, the area of our room, you don't have to use a calculator for this either, is 10 feet by 15 feet, is 150 square feet. Okay. All right, therefore, the illuminance is the lumens divided by the area. All right, and we get foot candles. All right. So now kind of look back at 2 weeks ago's content. Imagine in your mind 33 foot candles. What does that feel like?
Dimmer than in here.
Dimmer than in here. Yeah.
Not totally dark. Nice.
Yeah, kind of like a living room-ish. Yeah. Residential den, study, home office maybe. Yeah. All right. Yeah. Okay. Yeah. All right. So let's go the other direction. So we worked the equation one way. Now we're going to kind of use the same equation but work backwards. All right. How much light is needed in our space, and then how many fixtures are needed? Okay. You can see why this would be very useful, right? So we're going to talk about the same room. It's 10 feet by 15 feet. But we've decided that we want it to be an average of luminance level of 60 foot candles. All right, so everybody pause for a second and imagine, what does 60 foot candles feel like? Yeah, about like here. All right. Yeah. A little brighter than the last one. We're like, okay, we want it a little brighter. Okay. So how many lumens need to be provided in this room? How many lumens need to make it to the floor in order to create that 60 foot candles? Let's pause and let me walk you through this piece and then we'll pause and have you do it. So we have been working with this equation. Illuminance equals lumens divided by area. All right. You can rework the exact equation, right? The same thing. And to come up with the lumens needed in the room equals the illuminance times the area. Right? So make sure you can think of this as the lumens needed, you need to provide these lumens, equals the illuminance level target, right? This is our design goal, times the area. So let's pause and have you figure that out. How many lumens do we need to provide in this space? All right, let's see our answer. So our target illuminance was 60 foot candles. That was given. And the area of the room was 10 by 15. It's the same room. It's the same 150 square feet. Right? It's a small room. Therefore, how many lumens do we need to provide in this room? 60 foot candles times 150 square feet is 9,000 lumens. So we need to introduce or provide 9,000 lumens, all right, to get this average illuminance level that we are after. Right? 9,000 lumens. And then, how do we get those? How do we get those 9,000 lumens? We provide luminaires, right? We design luminaires, right? Let's assume we have now chosen a luminaire, and it will provide or emit 550 lumens. How many do we need in this space? We chose one. We chose a luminaire. It emits 550, and we need 9,000. All right. So we need 9,000 lumens divided by 550 lumens per luminaire. All right. So 16 and some, but you can't have like a third of a luminaire. That just doesn't work. You're going to slice it into thirds? No. So go ahead and round that up to 17, or depending on how solid you are with that 60 foot candles, if you're okay with 58 or something would be fine. You could round down too. As the designer, you get to pick. All right. For my quiz questions, round up. Okay? All right. So we've determined we need 17 of those specific luminaires in 150 square foot space to give us that 60 foot candles. Is that the luminaire that you want for that space? Probably not. 17 of them is a lot for a small room like that. It's a little ridiculous. Okay, so good to know that you use your common sense and you're like, yeah, no. So you might go back and pick a different luminaire. Yeah, they're like tiny little Christmas lights or something, right? They're not very big. Okay, so let's recap. It's just this one equation, all right? And you can work it forwards and backwards. Illuminance is the light that makes it to a surface divided by the area of the surface, all right? And we can switch that up, all right? If we're looking for lumens instead, all right, and work it backwards, we can say that lumens equals illuminance times area. But this nice, beautiful equation that is so simple assumes that all lumens provided or created by the luminaire are going to be functional. We call them functional. They're going to make it to the task surface. They're going to be useful. Oh, that's not actually true. All right. So let's mess up our nice, easy equation with some additional factors. All right. All right. And we're going to call them, there are two factors we're going to look at. And together they're also called safety factors. All right. So that's another word for these considerations that we're looking at right now. And they are the light loss factor and the coefficient of utilization. Right? And by including these in our calculations, we're going to make our calculations a little more realistic to the real world, okay, and not as ideal as that very simple equation. So, light loss factor. Not all lamps actually provide the rated amount of lumens, right? There's a little bit of manufacturing wobble. And there's actually a decrease over time. You'll lose some lumens. Lamps get worn out and a little bit dimmer over periods of time, right? And so we don't actually design for day one. we're trying to design for 2 or 3 years in the future, right? Assuming that our lamps and our luminaires have a 5 to 10 year lifespan, we want to design for a little bit further down their lifespan. And so their amount of light that they provide is going to dim just slightly. The second one is coefficient of utilization, and we're going to abbreviate that CU. All right. It turns out that not all the lumens that are created by a lamp, remember that the lamp is the name for the bulb, right? Not all of the lumens created by the lamp make it to the work surface. There's also some absorption by the surfaces of the room, especially if we're bouncing light around or in the actual housing of the luminaire, right? So, we have been using this very idealistic, equation, but we're going to complicate it up. Is that the word? Yeah. Anyway, with these two factors, LLF and CU. All right. And so our illuminance is now going to be lumens times the light loss factor times the coefficient of utilization, all divided by the area. So we're adding some extra factors into our equation. Let's look a little more deeply at these factors. Okay. Safety factors. So light output decreases over time. Up to 25% of the light output could decrease over the life of the lamp. Right? And so we use a multiplier to account for the future decrease in performance. So I kind of liked this graphic. So if we set our target illuminance at this level, and we provide exactly the target illuminance in our design, then over time, as that illuminance decreases because of the light loss factor, right, over time it's just going to go down a little bit. Then by the time you're at the end of your lamp life, you will have insufficient illumination, right? Because it decreases. So instead, let's come over on this side. Instead, we still have the same target illuminance. In my opinion, this is aligned with that one. But anyway, so we still have the target illuminance, and we actually include that light loss factor to bump it up artificially, right? And therefore, over the lifespan of the lamp, right, we never have we never have insufficient illumination. What we could have by adding all of this extra light are some poor effects, including glare, overlighting, light trespass, extra energy use, and an increase in system costs because we've bought more lamps or more luminaires to provide more lighting. But we need it because over time, all right, we don't want to have too little light. The solution for a lot of these is dimmers. All right. So at the beginning of the lamp's lifespan, you might use a dimmer to lower its actual illuminance. Everybody clear on why we need a light loss factor? Yeah. Light bulbs get old, right? Okay. So we need to kind of give a little boost to our original target illuminance to account for later on when the light bulbs are old. Okay. So there absolutely are complicated data about exact light loss factors for specific types of lamps and specific luminaires. We're not going there in this class. We're going to use a industry standard generic value. And we're just going to use it for all of our projects and our quiz questions. All right, and that is 0.85. Right. What does this mean? Our calculations will therefore expect only 85% of the light produced to actually make it to the room's surfaces. So we design not for how we want it to perform on day one, but for how we want it to perform a couple of years down the road. Right? So working with this equation, all right, that light loss factor right there, we're going to plug in 0.85. Sorry, shall I go back? Are you guys clear on this one? Okay to move on? Okay. So remember, we're still talking about safety factors and making our illuminance equation a little bit more realistic. And so this one is called coefficient of utilization. It turns out not all the lumens that are provided by a lamp, right, we're spending watts to produce lumens, but then some of them don't actually make it to the work surface. Right? So we're going to use a multiplier to account for the efficiency of a particular setup of lamp, luminaire, and location within the room. It is a ratio. It's going to be a ratio of the initial lamp lumens to the lumens that actually arrive on the work surface. Okay? And that's going to depend on a lot of specifics. So, for example, we've got a contact fluorescent lamp here, and it looks like we are given the color temperature. Not that relevant, but that's okay. Right? And it's going to provide 65 lumens per watt, right? So that's its efficacy. But once you put it in this particular housing, right, this particular luminaire, that coefficient of utilization is only 58%, and therefore we get a drop in efficacy. Okay. Yeah.
Is this a different equation also?
This is just describing what coefficient of utilization is. It's a drop in the amount of light that's being provided. Right? Your lamp is producing all of these lumens, but not all of them get out of the light fixture. Some are absorbed by the light fixture and turned into heat, right? Because those photons hit the luminaire housing and turn into heat. And some of them are absorbed by other surfaces in the room, right? That's what we're talking about, coefficient of utilization. All right, so you can have the exact same lights delivered with a high coefficient of utilization. Right? Most of the lumens produced by these lamps arrive at their task area. Right? In this case, it's an artwork. Or you can have light delivered with a low coefficient of utilization. Right? For example, if the goal is to light this artwork, would you do it with a centrally located indirect lamp? No, probably not. Okay? Because not much of this light is going to land on that particular work surface, that task surface. The task is looking at the artwork. Right? Okay. So coefficient of utilization can be high, can be low. All right. There is very specific ways to find the coefficient of utilization. You can calculate this with some information from your lighting manufacturer about your specific luminaire and lamp. You also need to know the details about the room, the space where you're going to put the lamp in the room. All right. including the surface reflectances of the different surfaces in your room. All right. So if you're putting the luminaire in a all white room, the light is going to bounce around and more of it's going to land on your task surface. Right. Now imagine a room with black walls. Right. And you have the exact same lamp. How much light is going to land on your task surface? Less, right? Less than in a white room. So they also will have you calculate, it's called the room cavity ratio, and it's all about how far away from your task surface the light is, right? And including those reflectances. Or in our case, all right, we're going to be, oh yes, that's very nice, okay, and use some generic values, right, because one semester course. Okay. So some generic values for coefficient of utilization. We need some different numbers depending on what kind of luminaire that you are using. So if you're using a direct downlight luminaire, like a recessed can light, all right, use an 85% value. Right? If you're using an indirect luminaire, right, realize that the light is going to bounce around before it arrives at the task surface, and so we're going to have a lower coefficient of utilization, only 50%. A spot luminaire or accent luminaire. Now, most of the light, because it's just aimed right at your task surface, most of the light's going to get there. So let's use a higher coefficient of utilization of 95%. And finally, any kind of wash or general ambient luminaire that hasn't been covered, all right, you might use like a 75%. Right? So somewhere in this range, depending on the type of luminaire that you are using. Okay. Can this be specifically calculated? Yes. And we mostly use software for that. Yeah. All right, you ready to practice? Here we go. Okay, here we go. Here's our equation. Illuminance was the light that actually makes it to your task surface, divided by the area of the surface. All right, we've seen that before, multiple times. Illuminance is lumens divided by area, but we're going to clutter this up a little bit and add in those other factors. So illuminance is lumens times light loss factor times coefficient of utilization divided by area. All right, so let's look at this example. We've got a room. It's 30 feet by 30 feet. It's got 24 downlight luminaires, each 2,800 lumens. So let's compare. If you do the lumen method without safety factors, how many foot candles are in this room? So we're going to go with this kind of a basic equation and say we want lumens divided by area. So we've got 24 luminaires times how many lumens they each produce, divided by our room size of 30 by 30. We end up with about 75 foot candles. Pretty bright. Okay. Now let's try the safety factors. And for our class, we're going to use those generic numbers. So I did tell you downlight luminaires. Right? So we're going to use the 85% coefficient of utilization. And we are using the generic light loss factor of 85%. Okay. So you take your same number of lumens multiplied by these two safety factors, divide by the area of the room, and we get about 54 foot candles. So you can see that this would be the ideal number, but in the real world, you actually get quite a bit less. So a fairly big drop. Questions? Yeah.
Do we always do the calculation
Yeah, so you're going to be working with this, all right, because we're a little more sophisticated. So if you get these questions on the final exam, it will be obvious which one to use. All right, I will not make you guess. Yes. We're not. We're using a light loss factor and a CU. And if let's go back. We had a generic light loss factor of 85%. Okay. And you're just going to use that for pretty much all of these, right? And you had a generic value for the CU, and we told you that it was a downlight. Therefore, it's 85%. It looks like the same thing twice, right? Yeah. All right.
But the safety factor, second one, brings it down to 54.
Yeah, so the question was, with this design scenario, right? This is what we want. We think but how much light is it going to provide in that room? Does it provide 75-foot candles? Ideally, but no. In reality, we have to assume that those light loss factors come into play, all right? And it's only going to provide 54-foot candles, so you have to design for that. Then you have to compare against your target illuminance. How much illuminance did you want in the room? Did you want 50? Did you want 80? Right? We didn't tell you for this particular problem, right? But that's the next step. You would be like, okay, well, was this the right design? And if it wasn't, if 54 was not enough for you, then you need to either add more luminaires or change the luminaire specification to something that gave more illuminance, more lumens.
So if I wanted 50.
All right, let's keep going. Here we go. The next question is, once you have a target illumination level, right? You decided how bright you want it in the room, and you've just done those calculations we just did, all right, to make a preliminary luminaire selection and figured out how many of them. Now the question is, how do you place them in the room? All right. So now we're talking about laying out the luminaire spacing. Many lighting designs, and we're talking about ambient lighting because we're still in the lumen calculation. All right. Many lighting designs will aim to place an even amount of ambient light throughout a space for general use. So how are we going to lay out the lighting plan to create this? You want to find the spacing interval, SI, fancy acronym for spacing interval. Right? This is going to be the maximum distance to put between each luminaire. So we'll find an interval and then we'll space them evenly. And we're going to define that as the center-to-center distance between fixtures in plan view. Right? So if you're looking at a lighting plan, you measure from center to center. So here's your spacing. And there's a couple of factors we need to consider with spacing. One is the height, right? Your ceiling height, your mounting height of the luminaire. And also, what kind of luminaire do you have, right? And we're going to call that its spacing criterion, SC. All sorts of new terms. Spacing interval, spacing criterion. Let's see how this works. First of all, let's talk about that mounting height. It's pretty easy to understand. And we're looking at, in this image, a interior elevation, right? So this is height, right? This is the floor of the room. This is the ceiling of the room, right? Mounting height is going to be measured from the work surface, because fairly often we're concerned about a desktop height or a tabletop height. So from the work surface to the bottom of the luminaire. In this case, they're showing a recessed luminaire, right? This is a recessed can light up into the ceiling. Right? So if you've got a recessed luminaire, the bottom of the luminaire, we assume, is at ceiling height. If we have pendants, that's going to bring it down. All right. And also, very typically, we will measure the work plane at 30 inches above the floor. That's standard table height in most desks, not necessarily drafting tables. These are a little higher, right? But for generic calculations, 30 inches is a really common work plane. Okay. So mounting height is going to be the distance, measured in feet, between the work plane and the bottom of your luminaire. Why do we care about spacing luminaires? Why can't we just throw in exactly the amount of luminaires we need for the light for that room? Well, if they're too far apart, they're going to look like spotlights with big shadows in between. If they're too close, the lighting can wash out the room, create glare, right? We want a nice even amount. So even if we decided that we needed to provide, 7,800 lumens for the room, right? We want 7,800s nicely, evenly distributed, right? And not just in one spot. Go back to our water analogy. We want those lumens to rain down evenly on our task surface, a gentle rain. We don't want a waterfall in one spot in the middle of the room and then nothing anywhere else. Okay? Just made that up. So there you go. Let's talk about spacing criterion. These are going to be specific to a luminaire, and you can tell why. Some luminaires are going to provide very direct, narrow beams, and some are going to provide wider beams, more indirect light. So the spacing criteria is usually a number somewhere between 0.5 and 1.5. If your luminaire provides symmetrical distribution, right, it'll only have one spacing criterion number. What does that mean? If it, and go for your water analogy again, if it sprays light in pretty much all directions equally, all right, we're talking about the plan view, all right, all directions of the plan view pretty equally, right, it's just going to have one number. But if it's asymmetric, all right, a luminaire with, this should say asymmetric. A luminaire with asymmetric distribution may give a spacing criterion in two directions, kind of parallel with and perpendicular to the luminaire. And we have an example of one of those in our room right here. Take a look at our fabulous lighting example. Right? This is a luminaire with asymmetric distribution, meaning that in this direction, all right, it doesn't actually provide much light. It provides light in this direction, east-west, but not north-south, okay? I don't know which direction is which, but anyway. And so this is an example of an asymmetric distribution, right? A lot of linears are asymmetric. And it might, the cut sheet, all right, the spec sheet might give two spacing criteria numbers. Why do we care? We care because we're going to use that spacing criterion to help determine our spacing interval. Remember, the overall goal is we're trying to lay out luminaires in our room, right? Not get them too far apart, not get them too close together. And So we're going to use a new equation. Okay. So the maximum spacing interval, the farthest apart that you want those luminaires on your plan, is going to be your spacing criterion multiplied by your mounting height. Remember what mounting height was? What's mounting height in this room? Just not the number, just define it. It's from here, where to where? Table height to bottom of the luminaire. Yep. Yeah. If we got a measuring tape, we could find that. But yeah.
We have a luminaire that's an asymmetrical distribution. We have to do calculation
Twice. Correct. One in one direction, east-west in your room. One in the other direction, north-south in your room. Bingo. All right. If you have no spacing criteria data, not all cut sheets are going to provide this. You will find, by the way, when you start looking for luminaires for your project, that luminaires designed for commercial use have tons of data available. Luminaires designed for residential use often don't have this photometric data available. All right, so maybe you don't have this information. What do? You're going to use a rule of thumb. All right, easy peasy. Here we go. We're going to space our luminaires at the ceiling height divided by 2. Wow, that was easy. So, for example, if we have a room with an 8-foot ceiling, we will space the luminaires roughly 4 feet on center from each other. Also, when you space them from the walls, they should be about 2 feet from the walls. Half of that spacing criteria. As another example, if your room has 10-foot ceilings, you're going to space the luminaires roughly 10 divided by 2 is 5 feet on center. Right? And make sure that they're about 2.5 feet from the walls. Right? Half that spacing. So let's look at these little diagrammy things. Okay, these little illustrations. And you can see why the ceiling height makes such a difference. So if we have 8 feet, we're going to want to fully cover our space with some overlap, and 4 feet is going to be appropriate. If we have a taller ceiling, kind of the cone of light is wider because there's more room for it to spread out. And we can actually space them a little further to give the same even coverage along the floor or the task surface. Rule of thumb, ceiling height divided by 2. So all of you doing residential work, that was easy. Yeah.
So if I have 100 foot,
Okay. Okay. If you are designing something with a 100-foot ceiling, Richie, I hope that you are going to do more impressive calculations than this. Okay. But what about a 12-foot ceiling? Look. Okay. Okay. Let's reel this into a little bit more realism. You've got a residence with one room that has a 12-foot ceiling, and you're proposing to light it with a series of evenly spaced recessed can lights. What is your spacing interval? How far apart would you place those? 6 feet. 3 feet from the walls. Thank you. Yeah. Mm-hmm.
so use the by 2 again.
Yeah. So here it is, half the distance. Don't put your luminaires too close to the walls. Right? And a rule of thumb for that is to use half of that spacing interval or center to center distance. So what you're looking for is a room that looks like this. By the way, I'm going to switch it to I should So over here, we have a room. All right, this area is evenly lit with this series of luminaires, and they're equally spaced. Here we have the same room, same equally spaced luminaires, but look at where the end one is. Too close. All right, gives you kind of a nasty hot spot. And so that's too close. This is better. The rule of thumb is half of the center to center distance. All right, here we go. Another topic. Are we good for it? I should have brought like treats or something. Okay. You have been introduced this semester to candle power measured by candela. Let's review, just in case. Candle power is the intensity of light in a specific direction. It's directional, right? It's like a ray. And let's use a water analogy because that seems to work for me. And we're interested in, let's assume this is a luminaire, and it is spraying out these beautiful lumens in all sorts of directions. I took this photo and I flipped it upside down because most of our luminaires are ceiling mounted. Okay, so it's the same photo, it's just flipped upside down. And so candela is measured in a specific direction. So this candela would be different than this one. Those are two different measurements, even though it's the same luminaire / water fountain, right? And the total amount of lumens, right, is spraying out from this luminaire, but now we're measuring in a specific direction. This is my attempt to be clever. All right. So candle power, the intensity of light in a specific direction. Illuminance, remember, is the amount of light falling on a specific surface. So why are we talking about this? It's because we've switched from talking about ambient lighting to now we're talking about task lighting, where we're interested in a very specific surface. So this light fixture is like a water fountain spraying out lumens, and we're interested in not the total amount of lumens. We're interested in the ones in this direction that hit this task. That's what we care about. So back to our water analogy, we're interested in what ends up in this glass. Right? Not all of the rest of the lumens, not all the rest of the water coming from our water fountain. You've seen this slide before, making sure that we understand candle power can vary depending on the type and the distribution of the lights. So a focused spotlight might produce the same amount of lumens as a wide indirect or floodlight, right? Same amount of lumens. And yet the candle power in this one direction we're measuring, right, will be different. Right? We have more for the spotlight and less for the floodlight. Okay. Photometric data. Told you this was a heavy lecture today. Photometric data. What are they? They are numeric information about a luminaire and its performance. You've had the experience here in this class of reading a cut sheet, right? And you saw some of the photometric data, like how many lumens did it produce, what was the color temperature, those kinds of things, all right? And we need this kind of information in order to design the appropriate amount of light for your space. This is really important for sustainable design because we don't want to provide too much, right? And for economy. And the photometric data is typically on the spec sheet or cut sheet. All of these lamp characteristics that we've been talking about are photometric data. Light output, efficacy, illuminance, candle. Here is an example of a photometric, a set of photometric data that might be on a cut sheet. In this example, which is coming from a, let me put the textbook name, from the Fundamentals of Lighting textbook, right? We're looking at this luminaire, so just kind of a little picture to show you what that looks like. All right. In the space, it looks like this. And here's all the kinds of numbers that might be on the cut sheet. So we're going to look at each of those types individually. Starting with candle power. Right. So this is the same information that was on the last sheet. All right, I just made it bigger so we can focus on it. So candle power can be shown as a graph. We've seen candela distribution graphs before, the polar graphs about which direction and how much light is going in each direction. These graphs will show the direction, pattern, and intensity of light distribution from the luminaires. To read them, you're going to assume that the light source is right here kind of at the center. Okay? And you're going to identify a specific angle that you're interested in. All right, maybe you're trying to light something that's over here at 30 degrees angle from your luminaire. And then you read the graph by finding this line and its intersection with your angle. And then you can judge that candela. Notice on this graph it's somewhere between 1163 and 1550. Okay. Looks like halfway between. So what is that, like 1250? Am I right? Something like that. Okay. It's not super accurate, right? You're not going to get an exact number by reading the graph. You're going to get an estimate, right? But the graph is super useful to visualize this curve. Notice they only give you half of a graph. They might do that if it's symmetrical. It's not even important to give you the other half because it's the same, right? So it's symmetrical distribution, left and right, or east and west, whatever you might call it, and we would just read it for 30 degrees in either direction to be this number. Now, if that is not enough information for you, you need a more specific number. Right. Oh, hold on just a second. I forgot to mention, when you are reading this graph, the numbers on the rings are always going to be different. Why is that? Why are these weird numbers? Why aren't they like 200, 400, 600, like something even, right? It turns out they scale the graph to the luminaire, so the maximum candle power will always be the exact number at the widest ring. So if the question is, what is the max candela produced by this luminaire, you would immediately go, it's 1550. Right? And then they set it up at 25%, 50%, 75%, 100%. That's how the graph is produced. It's not going to be the same for every luminaire. Okay, so say we want a more specific number for that candela at 30 degrees. You can work with a candle power summary table, and some manufacturers will provide this. Okay, it's more accurate. There's no interpolation and say, oh, it's about halfway. All right, no. So would we read this? Vertical angle of 30 degrees. Right? Horizontal angle of, we're going to read for 90 degrees, right? Because it is 1334. Okay, I can see where that would be 1334, halfway in between 1163 and 1550. 1334, that's our number. That is our candela. So yeah. So if you wanted to do another angle, and measure at 45, 30, 40, 50, 60. So 45 would be right in here, right? And we'd measure it, and it looks roughly halfway in between 775 and 1163. So 1,000. Yeah. So coming over here, I'm totally wrong because 45 gives you 884.
Yes.
I'm reading this wrong. Do we want the 0 angle or the 90 angle? No, we definitely wanted the 90 angle. Okay, I told you right. Okay, another way to do this. A lot of times you're going to literally point a spotlight at your task surface. So measuring over here at an angle is not really useful. You really only care about the candela in one direction, and that is directly where the light is pointing. Right? Because you're literally going to aim the spotlight at your artwork.
Is that what we're looking at? Light problem?
It is not, unfortunately. So, in this case, a lot of the spotlight lamps will give what's called a center beam candle power number. Rather than give you all of this other data, they're like, you don't care about that. You only care about candela in one direction, and that is directly down the pipe, directly down the center of the luminaire. Right? And so they will only give one number, and that is the candela pointing directly away from the luminaire. Right? It assumes that the luminaire is aimed at the focal area. This is really common for accent lamps. Right? And it's going to look like this. It says CBCP, center beam candle power. And that value will be in candela. So this is what that kind of photometric data looks like, right, and how to read it. Let's take a look at some more of these candle power graphs. We've seen them a couple of times this semester, so hopefully this is starting to get familiar to you. Right? And so you might have a different distribution diagram for a diffuse source, right? And it's shading in all sorts of directions. Or a directional source, more of a spotlight. Most of the light is going in one direction. We talked about the different types of luminaires, direct, indirect. Right? So here is a direct, indirect. In this case, the light is shining equally up and down these distributions. All right. Since our focus today is calculation, how do you tell how much light to put on an accent surface such as an artwork hanging on the wall? The first thing we need to do is set the target illuminance for that object. And there's no IES recommendation. It doesn't say that you need 30-foot candles on an artwork. Right? It doesn't say that you need 1,000-foot candles on an artwork. Instead, we need to talk about contrast. So we want to light a focal object with somewhere between 2 to 5 2 to 5 times the illuminance of the surroundings in order to make it pop. Right? It's not about total illuminance, it's about the contrast between your target, all right, your piece of artwork, and their surroundings. So you want at least 2 times in order to create visual interest. Avoid more than 5 times because then it's like, whoa, all right, too much. Extreme drama, maybe. Okay, if you're going for extreme drama, you can go ahead and play with that. But 2 to 5 times is a comfortable highlight. All right, an accent. So, for example, here we go with the numbers again. Ready? Okay. You would like a dining room to have an overall ambient glow. All right, your ambient light in the dining room of 10-foot candles. Let's all think about 10-foot candles. What does that feel like? Okay. It's dim. Yeah, it's relaxed. It's cozy. And then what illuminance should you give to an art object in this room? Give us a range. It's not that hard. It's not a trick question, guys. I literally give you 10-foot candles. Okay, so anywhere from 20 to 50-foot candles will make this object be an accent. It'll make it pop. All right, and you get, as the designer, you get to pick depending on the actual object. Like if it's shiny, you might actually kind of dim that down. Or if you're like, man, this is really important, and bring it up to that 50-foot candles. Right. But the rule is that we are interested in the contrast between our accent object and the rest of the room. All right, so we've set our target illuminance on our art object. Now let's talk about how to create that target illuminance. How are we going to get there? We're digging down. And one really common way to do it is to shine a light at it. Okay, all right. And a preferred angle to your artwork is roughly 30 degrees. If you put your light source too close, you're going to kind of wash across the front of your artwork. Might be good if what you're trying to do is show texture, but probably not. All right. Depends on exactly what your artwork is, but it's better to bring it out a little bit. All right, so you get about 30 degrees. And that 30, you can measure it because of, geometry and equal angles. You can measure it from the wall 30 degrees over to the light. Or you can measure straight down from the light 30 degrees over this direction. Right? Those are equal angles, yeah. Bringing a little geometry into our classroom today. You can, of course, bring it out further, right? But you end up not getting the highlight that you want. Right? So about 30 degrees. Over here we have an illustration of an accent light pointed at a wall. And when we were talking in the last slide about center beam candela value, they're talking about the light that is pointed right down the center. Measuring that piece right there. And we're going to point that center beam at 30 degrees. Here's a couple more rules for spacing while we're talking about this. And it's the difference between wall washing and wall grazing. Wall washing attempts to evenly illuminate a particular wall. Maybe the whole wall has some a series of artwork. Maybe you want to highlight a particular area, all right? But you want to wash that wall with light. For wall washing, you want to move that luminaire, right? And they are asymmetrically producing light, but you want to move that luminaire about a third of the room height. So if your room is 9 feet tall, yeah, move it about 3 feet away from the edge while washing. Yeah. Nice even coat of light, right? Spread all around your room. Wall grazing. Wall grazing is a little bit different effect. It's just kind of dribble light down the wall, and it's really used to highlight texture. Okay? And I know we saw some examples in our field trip. Yeah.
Not downlights, right? For the wall washing.
So you can use a light that has an asymmetric distribution and get this, all right? Or you can use a regular downlight and you'll get this area illuminated as well. It depends on what you want. If all you want is on the wall, then you use an asymmetric one. Yeah. All right, so wall grazing, you're going to move that closer to the wall within a foot. So pretty close. And that's if you want to highlight texture. Don't do it if you've got a drywall, regular sheetrock drywall. You'll just see every tiny little imperfection. Right? Don't do it if you are have a tile wall. Most tiles will have imperfections that will really show up under this wall grazing. Do it if you have a beautiful stacked stone wall, concrete wall, something that you want to highlight the texture. Oh, I didn't realize I had an example here. Okay, so this one right here, wall washing or wall grazing? On the right-hand side. Are we highlighting? I'm talking about the white wall, the museum on the right. Are we highlighting the texture of the wall, or are we just providing even illumination all over that wall? Yeah, that one's wall washing. Okay. What about over here on the left? This wall right here. Wall washing or wall grazing? Grazing. Yeah, this is going to be grazing because look, we're casting these shadows. That's what wall grazing does. Mm-hmm. All right, we've covered the lumen method, all right, for all sorts of horizontal calculations. We've covered some vertical considerations, and there is now a calculation to go along with. Okay, it's called the point-by-point calculation, and it's used to determine the illuminance level for a focal point. Right, and we've been looking at those. Those are often vertical. They can also be horizontal. If you had, and the example for horizontal is if you have a lovely sculpture sitting on a, yeah, I want to highlight that. Point by point is going to be used for accent and task lighting. Just like the lumen method, we can kind of run it forwards and run it backwards. So you can solve for the illuminance level and determine how much light is being provided by a given lighting design. So you've already designed it. You're like, I'm going to put this light and highlight this artwork. Does it work? Is it good? All right, let's find out. Or alternately, you kind of run this backwards and solve for candela. Determine how much light is needed, and then how many or what type of fixtures are needed. And these are all going to use the same formula. Illuminance equals candela value divided by distance in feet squared. And we can write that shorter as illuminance is E equals, it looks like a number 1. I don't like this. I write my L's with like a loop so that it's not a number 1. But anyway, it's a lowercase l, right, for luminous intensity in candela, right? Illuminance equals candela divided by distance squared. Candela. I like to, when I was trying to remember this for myself, I like to go, oh, that looks like a little candle. I mean, the L. All right. Why distance squared? Okay. Well, it turns out that illumination is going to decrease the farther a surface is away from the light source. But it doesn't decrease linearly, right? It decreases using the inverse square law. So when we're measuring the distance, imagine stretching a string from your light to the luminaire. So this would be the distance. But the drop off in light level is actually related to the square of the distance from the light source. It's not linear. It is related to the square. All right, so let's try it. And we're going to use the simplest scenario. It's not up on a wall, right? So we don't have to measure angles. We're not doing angles. We're doing one luminaire, and it's shining on a beautiful museum-worthy plate. All right. So, sitting on a table in the middle of the room. And we're going to light it with one luminaire. We've got a 10-foot ceiling. The plate is at 3 feet above the floor. That's the height. 7 feet, right? That distance from here to here, 7 feet. And that luminaire that we have already chosen has a center beam candle power, CBCP, of 10,000 candelas. So what illuminance level can we expect at that plate? Let's use this formula. We're going to solve for E illuminance, and it's going to be candela divided by distance squared. I'll give you a second. All right, let's plug it in. Our candela value was 10,000 candela. Our distance was 10 feet minus 3 feet, 7 feet, right? 10 feet minus 3 feet, 7 feet. That was our distance. Okay? So our luminance is 10,000 candela divided by 7 feet squared. It's 204 foot candles. The only tricky thing, well, also tricky things, but one tricky thing to watch out for is that distance is measured in feet. So if you, for example, have a work height of 30 inches, remember that that's 2.5 feet. All right. So it's 2 foot 6 inches. It's not 2.6. That's 2.5 feet. All right. I see that mistake all the time. Okay, 204 foot candles. Is this enough on the plate? Well, maybe. It depends on what's in the rest of the room, right? Remember, we want that to be 2 to 5 times more than the illuminance in the room. And so if we had an illuminance in the room of 70 foot candles, it's a fairly bright room, right? Then this would be solidly in the middle of that accent lighting range of 2 to 5 times the surrounding room, and we'd be like, yeah, that's good. Okay. Oh, I forgot. That was all on the next slide. Here we go. Okay, double check. Will this design actually give visual interest to your artwork? This beautiful museum quality plate, right? You need to know the ambient illuminance. So this is a museum space, and IES recommends 30 to 50 foot candles, right? And we want a nice dim. 30 is not that dim, right? We want a lower level of 30 foot candles. That's what we've decided as lighting designers. So what illuminance should you give to an art object in a 30-foot candle room? Use the 2 to 5 contrast rule. Anywhere from 60 to 150 foot candles will make this item pop. But you can also divide 204 divided by our 30, and it's roughly 6 times the contrast. So it's really going to pop. All right, this is a high illuminance level, but it's within reason for a really special object. All right, it's going to be quite bright. And a caveat, that 204 foot candle is only going to occur right in that hot spot, right in the middle, center beam. Right, it's going to fall off slightly. It's okay, this is a small object. 6 times, we got that? Okay. So, more often,
So 6 times is more, right? So we would want to reduce.
yeah, so if you are uncomfortable with the 6 times, if you as a lighting designer were like, oh, I don't want 6 times the contrast on this object, it's not that special. I mean, it's special, but it's not that special. What you would do is say, oh, that's too much, and you would choose a different luminaire, right, that had a lower candela. You'd just go a little bit dimmer. Correct. All right, more often we want to do the opposite and kind of run this equation the other direction. More often we want to find out what candela is needed and then select the right luminaire rather than already having selected the luminaire and finding out what candela it's going to produce. All right, so more often we want to go this direction. Let's take a look at an example. An accent luminaire, recessed the same 10-foot ceiling, and it's above the same plate, it's on the same table, 3 feet above the floor. All right, same room, same plate. And we've decided we want to illuminate that plate to 150 foot candles. Remember that we just calculated over here that 60 to 150 foot candles will make this item pop. So we want to go a little lower than what we were doing, just like Richie was saying. All right. So if we want to illuminate that plate to 150 foot candles, which luminaire should we select? We need to calculate the center beam candle power value and then pick one that matches. Okay. So let's run this equation the other direction. We know that illuminance equals candela value divided by distance in feet squared. And in this case, solve for candela. Solve for L. Let's see if you can do this. I'm going to say when I'm doing these equations, I always write my L's like this, because otherwise they look like ones. So just so you might want to take take that tip.
172.
All right, let's solve it together. Here we go. Here's our equation. E equals illuminance equals candela divided by distance squared. Let's rework that equation and solve for candela. It's going to run candela equals illuminance times the distance squared. Okay. We decided that we wanted 150 foot candles. We know that our mounting height between our object and the luminaire is 7 feet squared, right? And so we're looking for a luminaire that meets this criteria. 7350 candelas. The other one was a little too much, in our opinion. So let's pick this one. So you can see that you can run the equation kind of forwards and kind of backwards, depending on where you're going with your design process. So you as a lighting designer decided that you wanted 5 times the ambient illuminance of the room on this particular art plate. Let's go back. Let's set this question up. All right. So the IDS recommendation is 30 foot candles, or 30 to 50. We decided 30. And then with the last example, we found that light created 204 foot candles. That was 6 times contrast. And we decided in our design that was too much. So what would give us 5 times contrast? What would give us the 150 foot candles? That's what you're now calculating. We didn't like the other luminaire. We didn't like that lamp. It was too bright. And so we want to select a different one. And we're aiming for 150 foot candles, because we think that's going to give 5 times the contrast with the rest of the room, and that's what we have decided that we want. Okay? And so we have the same distance and 150 foot candles, and we're going to plug that in. So you take your equation and you solve for candela instead this time. You plug in your 150 foot candles, that's your target illuminance. That's the distance squared. And you end up with a target candela. So now when you go look at cut sheets, you're like, which lamp should I choose? Should I choose this one? Should I choose this one? Should I choose this one? I need one that gives in the range of, you're probably not going to find exactly this number, but in the range of 7350 candela. Whew. Does the quiz make more sense now? Yeah. Okay. All right, I'm going to pause our video. Hi, everybody at home.